Okay, test review. Bonding, unit 11. All right, let me expand this out. Okay. Label the following as ionic, covalent, or both. All right, so what you're looking for here is if it's ionic, it will be a metal and a nonmetal. If it is covalent, it will be a nonmetal and a nonmetal.
All the members of the girls' basketball team, please report to room 124. With teacher permission, the girls' basketball.
All right, so a nonmetal, nonmetal, and then both will be a metal bonded to a polyatomic ion. And so we have chlorine, oxygen, nonmetal, nonmetal, covalent. Potassium chlorine, so metal, nonmetal, ionic, and then iron and sulfate, which would be a metal and a polyatomic ion. So the polyatomic ion will be held together with covalent bonds, and the metal and the polyatomic ion would give us a ionic bond. So you'd have an ionic and you'd have a covalent, so both. And I'm just turning around here. I'm going to grab one of the reviews in my hand. Because I didn't leave my enough. Yeah, actually, I'll just do it here. I'll just squash it all in there. All right, so next section is give the dot diagram, the number of bonding and non-bonding pairs. So we have dot diagram, bonding and non-bonding pairs, angle, electron arrangement, geometry, hybridization, polar, nonpolar, and draw the 3D shape. Holy cow, that's a lot of stuff. All right, so I'm not going to do all of that there. You can refer to the VSEPR sheet for the number of bonding and non-bonding pairs, and you can get the electron arrangement, and you can get the bond angle, and you can get the geometry. So I'm not going to include those here because once you know the number of bonding and non-bonding pairs, you could get that. And also, I'm not going to ask you to write all of that down on the test. I am simply going to ask you for the dot diagram, bonding and non-bonding pairs, the hybridization, polar, nonpolar, and the 3D shape, though. So I'll do those. All right, so here we go. I'm going to count the electrons. Try not to mess any of these up like I did the other day, hurrying up. We have 6 because of oxygen, so group 16. So 6 plus 14 gives us 20 electrons. So I have, let's see, if I go to this side, I'll just do it under it. So I'm going to do the I's, finish the octet of the I's, so dot. I'll do that for the first one. I'm not going to do that for the others. I'm just going to know that they're there. So that's 16, 17, 18, 19, 20. So I have done the dot diagram, the first part. The second part is how many bonding and non-bonding pairs? It's 2 bonding, 2 non-bonding. The 2 and 2 add up to 4, which gives it an sp3 hybridization. 7th period students, you don't have to do the hybridization. And then the last part is it polar or non-polar? Well, this is going to be polar because of the non-bonded pairs. I have them lettered going down, so I guess I'll go in that direction next. Let me switch colors so in case it blends together. All right, so we have 7 plus 21 gives me 28 electrons this time. All right, so 28 electrons. I, 3 CLs. Finish the octet of the CLs. That's 24, 25, 26, 27, and 28. So we get 3 bonding, 2 non-bonding. 3 and 2 will give us a total of 5 effective pairs, which gives us DSP3. All right, now for polar in this one, this is one of the exceptions. This would be non-polar, even though it has unshared pairs. Why? Well, because it's symmetrical. I forgot to draw the 3D shape of that first one. I'm definitely going to run into issues drawing that. Why don't I just do that when I'm finished, and then we'll be able to relate it to all of them. All right, so 8 plus 14 is 22 electrons. Xenon bonded to an I and an I. So that's 16 finishing the octet, 17, 18, 19, 20, 21, 22. So 2 bonding, 3 non-bonding. 2 bonding, 3 non-bonding will give us DSP3. And once again, that would make it non-polar because of the symmetry. Now that I'm on that subject, remember this was a special one there that I feel like it should be non-polar. I found one issue where they did say, or one website which did say it would be non-polar, but the rest are saying it's polar because it would be T-shaped, not the way we were doing it with the 3 in the center and then the above and below for the electron pairs like they would be in letter C. All right, back to the next one then. We have 8 plus 4 is 12 electrons. 12 electrons, remember when we have more than one carbon, we have the carbons in a row like that. We're going to separate the 4 hydrogens, so 2 and 2, and then we end up with a double bond in between. So 2, 4, 6, 8, 10, 12 electrons used. Very good. Remember, when you count these, you have to give the number of bonding and non-bonding pairs around each carbon. So around this carbon, remember, you count double bonds only once. So we're going to say 3 and 0 and 3 and 0. So they're both 3 and 0. The hybridization then would be sp2. And this thing is going to be nonpolar because carbon-hydrogen bonds are considered nonpolar bonds, remember. All right, next one, SeO. We have 6 and 6 is 12 electrons. This one ends up like so. So we have a double bond between the Se and the O. When you don't have a central atom, you don't do the number of bonding and non-bonding pairs, nor the hybridization. But this thing would be polar because it's not diatomic. So we have 2 different elements. It's going to cause a polar bond. C3H6. Let's do 2 there, 1 here. So 1, 2, 3, 4, 5, and 6. So that carbon's good. This carbon would need a double bond there. And then we've used up, let's see, 12, 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used up all the electrons. I used the wrong color. Oops. The number of bonding and non-bonding pairs. So carbon 1, carbon 2, and carbon 3. The first carbon has 4 and 0. The next carbon has 3 and 0. And the last carbon has 3 and 0. So we're going to have an sp3 hybridization around that and an sp2 hybridization around those two. But the whole thing, again, would be nonpolar. All right, SO2 minus 2. So we have 6 plus 6 times 3 is 18 plus 2 is 26 electrons. I'm going to do it over here. Let me see if I can see where my camera ends. All right, so S, I just made an 8. S with 3 O's. Finish the octet of the O's. That's 24, 25, 26. So I have 3 bonding, 1 non, which would make it polar. sp3 hybridization. Again, a total of 4 effective electron pairs. PCl5. So 5 plus 35 is 40 electrons. P with the 5 iodines attached is 40 electrons. So this is 1, 2, 3, 4, 5 and 0. DSP3 and nonpolar. The next one, Se is 6 plus 28 is 34 electrons. Se, finish the 4 iodines, that's 32, 33, 34. 4 and 1. Once again, DSP3. This time, though, polar, non-shared or a non-bonded pair. Switch colors. 4 plus 2 is 6. Plus 14, we have 20 electrons. Carbon bonded to 2 hydrogens and 2 chlorines. So 16, 17, 18, 19, 20. Or no, 16. Yep, that's 20 electrons. All right, good. So we have 4 and 0. It would be sp3. But this time it's polar because it's not bonded to the same thing around. Though my picture, in 2 dimensions looks symmetrical, in 3 dimensions it's not going to be. Anytime you don't have the same thing bonded on all 4 sides, or as in the next one, all 3 sides. So Al bonded to 2 Cl's and an F. Notice Al lacks an octet, but it's supposed to lack an octet because it's in group 13. And so we get 3 and 0, which is an sp2 hybridization, but polar because it's not bonded to the same one. I had that one on the quiz, if you remember. H2, we're going to bond the O's together. We end up with an extra pair around each one. Once again, just like adding the carbons, there's not just one in the middle. This one's a center oxygen, and then this one is a center oxygen. So around this one, it's 2 and 2. Around the other one, it is also 2 and 2. They would both be, though, sp3 hybridizations, and this thing would be polar because of those non-bonded pairs. SNF2, I'm kind of cheating there. That would really be an ionic bond, but 4 plus 14 is 18 electrons. Is that right? Let me look at my periodic table here. Yeah, group 14. So yeah, 18 electrons, 16, 17, 18 electrons. We have an issue here, and that is Sn is in the middle, like Al and like Al was, and up there, I guess that's the only one we've done so far, where it does not have an octet, but it does need an octet, and so we're going to have to either make a double bond on one side, or we could make a double bond on both sides and make it symmetrical. It doesn't really matter which. We can only kind of double bond once, so this is 2 bonding and 1 non, which would make it sp2 hybridization again, and I forgot to change colors again, and that would make it polar because of that non-bonded pair. Carbon monoxide ends up with one that looks like that. Remember, no hybridization, no number of bonding and non-bonding pairs, but it would be polar, and I forgot to change again. Oops. What can I tell you? I want to get this over with. All right, so we have C2H6. We have 8 plus 6, 14 electrons. Carbon bonded to a carbon. Spread the hydrogens out evenly. Each one gets 3. Everyone has their octet. Everyone's happy. We have, remember, 2 different carbons. Carbon 1, carbon 2. So we have 4 and 0, 4 and 0. They both have sp3, and this would be, once again, non-polar. Change color. Haha. Carbon, triple bonded to carbon this time. 2 hydrogens on either side, or the 2 hydrogens will distribute evenly. We end up with, once again, carbon 1, carbon 2, 2 and 0, 2 and 0. sp hybridization, non-polar, due to the fact that they're all oxygens and hydrogens and carbons. 4 plus 42 plus 2. So that's 48 electrons. Si in the middle, bonded to 6 Fs. 1, 2, 3, 4, 5, 6 Fs. Put it in brackets because of the charge. And we end up 6 and 0. D2 sp3 and non-polar. Xe, 8. 7 times 4 is 28. That gives us 36 electrons. When we fill our 8 on the Fs, that's 32, 33, 34, 35, 36. So we end up with 4 bonding and 2 non-bonding, which is, once again, D2 sp3 hybridization. Non-polar again. That's one of the exceptions. The 4 chlorines would be in the same plane in the middle, and the unshared pairs above and below, which would give us a symmetrical molecule, therefore non-polar. CO2 we've done enough times, you might have that one memorized. A very common one to do. We have 2 and 0. Remember, double bonds count once, so 2 bonding, 0 non. sp hybridization and non-polar. And then BIP, again, I cheated. That'd probably be ionic anyway, but we end up with that. Once again, no hybridization. No number of bonding and non-bonding pairs because there is no central atom, but this thing would be polar, and we made it through that. Let me add a page here in the back. We'll do the 3D shapes. All right, so our 3-dimensional shapes here are going to be, if you have 2 and 0, the only thing you could possibly have is that. If you have 3 and 0, you're going to have a central atom. Oh, I'm sorry, 2 and 0. 3 and 0. So those 2 are planar, meaning they're flat. 4 and 0, 3 and 1, or 2 and 2 are all sp3 hybridization, and you end up with the one coming out of the board and the one going into the board. The difference will be if it's 4 and 0, these are all going to be circles for show atoms. If it's 3 and 1, then you just take away one of these and put a non-bonding pair. So 3 and 1, the difference will be, I should have left myself some more space there again, like always. Let's put the non-bonding pair there. Doesn't really matter. There's no real convention, but remember, we stick that extra pair of electrons is going to have more density, bigger space. And then the 2 and 2, again, we'll put the 1 electron pair there. We'll put the other one here, and then we'll have, the one coming out of the board, the one going into the board. And it does affect the bond angle and things a little bit, but for our 3D shape, that's good enough. So we have that sp3 hybridization. The flat part of this being in the plane nose, and then the one coming out of the board, the one going into the board. All right, so then 5 and 0, or 4 and 1, or 3 and 2, or 2 and 3, we have the one above, the one in the middle, the one down. So those are in the same plane. And then we have this one in the same plane, and then one coming out of the board and one going into the board. Remember that center part right there, they'd be 120 from each other, 90 degrees from those, and these are 180 from each other. So that's 5 and 0. 4 and 1, once again, we just take one of those away. Let's say we take away the top one. So we have that electron pair down, coming out, going in, and then again, that extra electron density. 3 and 2. All right, so that's those two. This is the one that we sort of have an argument about, and that is, when I did it, I showed you an electron pair spreading themselves out like so, and then this one, the one coming out, and the one going into the board, all being in the same plane, therefore symmetrical. But like I said, I haven't been able to, prove that 100%, and so I would accept either polar or nonpolar for that one. But for this one, definitively, yes, it is nonpolar. We have the one above, below, and then the electron pairs in that 120 arrangement in the center of the atom, like so. Remember, you will have some Play-Doh and some toothpicks if you're still struggling with those shapes a bit. 6 and 0. Let me arrange those a bit more. So 6 and 0, we have the one above and the one below. So now we have 2 coming out towards us and 2 going into the board away from us. So there's that, they're 90 degrees, that octahedral shape. Same with 5 and 1. The difference again being we take away 1. So one coming out, that one's still down there, another one coming out towards us, one going in, another one going in, and then again that extra electron pair making that polar. And then 4 and 2, the other exception we discussed, where you have the extra pair of electrons above and below. So then the 4 are going to be the ones that are 90 degrees from each other coming out of the board and into the board. Sorry. And this one would be the nonpolar one there. So that's a nonpolar exception. The other one was, this is a nonpolar exception. And the other nonpolar ones then are if you don't have any non-bonding pairs. So nonpolar, 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 and nonpolar there. So they are the ones that we've discussed primarily. And again, the 3D shapes, you'll have the Play-Doh and the toothpicks if you still haven't quite have this figured out to play with when you're figuring out the shape on the test. All right, so back to the review here. Now some questions. Draw 2 resonance structures of ozone and benzene. So ozone, O3, gives us 18 electrons. You finish the octet, and remember, you end up with that structure. So we have to fix that structure because the oxygen in the middle does not have its octet. So we take a non-bonding pair from an outer atom and we make it a bonding pair. So there's one structure. And the other structure is, instead of doing it from the right, you do it from the left. So double bond there, like so. So there's the 2 resonance structures of ozone. And remember, the overall structure, the real structure, would be an average of those 2. Benzene in a ring, you have 6 carbons bonded to each other in a ring. Do the same thing with the other one. Designate maybe the top 2 as carbon 1 and 2. So this one has the double bond alternating between 1 and 2, and the other one has it exactly the opposite. So again, we put it in brackets. A double-headed arrow would fit between there, and the hydrogens would be coming off of the carbons. We just make it easier the way I have it. All right, arrange the following polar covalent bonds from least to most polar. So most polar is going to be the greatest difference in electronegativity according to the trend. And the trend is it decreases as it goes down and it increases as you go across. So we're looking for the one that have the greatest difference. And rubidium is going to be at a lower electronegativity than lithium is. And oxygen's higher than both of them. So this one is going to be the greatest difference. So this is the most polar, and down here would be the least. If I ask this, as I did on the quiz, the most ionic, that would be the same as this, the greatest difference. If I asked for the most covalent, it would be the exact opposite because it would be the least difference. All right, explain the picture in terms of bonding and electronegativity. This is a nonpolar covalent bond, equal sharing. This would be an example, Cl2. So that would be letter A. It's a diatomic where the electronegativity difference is 0. So the electronegativity difference is 0. A difference of 0. A covalent bond is what this would be. So it would be a polar covalent bond. And then we consider this last one to be an ionic bond. And so HCl, that's going to be B, and then the last one is going to be C. Explaining my choice, this is ionic, this is covalent, and this is nonpolar covalent. So the difference in electronegativity is 0. This would be a somewhat of a difference in electronegativity, and then this is a large difference in electronegativity. So list the pictures in order from greatest difference would be C to the least difference, which would be A. What is the significance of 1.67? We're talking there, if you know the electronegativity values, you can subtract them, and that would be a 50-50 bond, meaning it's going to be equal parts covalent and ionic. The greater than that, so if we have a difference greater than 1.67, then it's ionic, and then if you have a difference less than the 1.67, it is covalent. What are the properties? The properties are they're crystalline. These are right in your notes. They're crystalline. They have a high melting point. They tend to be between metals and nonmetals. They have positives and negative ions. They're held together with the electrostatic forces. Just make sure you look over your notes. They tend to be solids at room temperature because of those high melting points. Covalent bonds tend to be liquids or gases at room temperature, very low melting points. They're brittle. They're not crystalline. Ionic bonds are conductors, remember, in the molten form or dissolved in water, but not in the solid form. Covalent bonds are insulators. They're non-conductors. The molecule dance, once again, that's in your notes as well. That would be where the bonds are constantly in motion. They're flexing in that direction. They're stretching either symmetrically or asymmetrically in that direction. And also they are rotating. So the molecule dance is you hold your arms out, there's your head, and you do the molecule dance just like water. As I said, someone in first period requested that I put as one of the questions on the test, stand and perform the molecule dance. And so I'll be perhaps considering that and watching for it so that I can laugh, of course. It's all about me, remember. All right, so IR and microwave radiation, I put that in here because someone said we didn't learn it. So there's the notes. Came right from your notes. IR radiation affects the vibration of the molecule and can be used to determine the identity of the molecule. Microwave, so IR radiation affects the vibration and can be used to do the identity. Microwave radiation affects the rotation of the molecule, and it can determine the location of an atom in the molecule. So once again, right there from our notes. Let me go back to, so this is again right in our notes. All right, so calculate the formal charge and also do the resonance structure. So I have draw 3 resonance structures. NO2 is 5 plus 18 plus 1, so that's 24 electrons. So the skeletal structure of this that you draw is right there, where we have not an acceptable Lewis structure, even though we've used up all the electrons, because the N in the center does not have its octet. So 3 different resonance structures will be do a double bond on the right side, the left side, put it in brackets, or the bottom, or the right side. Don't forget the charge on the outside on this one. So then for formal charge, remember formal charge is the number of electrons on the free atom minus the number that are associated with it in the bond. I'm just going to put the dots on this one structure so that I can count them. For the doubly bonded oxygens, there are 6 minus the 4 plus half of 4, which is 2, and I get a 0. So I get a 0 for the doubly bonded oxygen. The singly bonded oxygen, 6 minus 6 plus 1 gives me a -1 charge on the 2 singly bonded oxygen. And then the nitrogen in the center, 5 minus 0 plus 4 gives me a positive 1 charge on the nitrogen in the middle. And all of these are exactly the same, so I'm not going to do the formal charge for the others. And so which of the, if I had to choose a best between those, there wouldn't be a best. It would be, they're going to be exactly the same in terms of formal charge. All right, SO4 minus 2, so we have 6 plus 24 plus 2. That gives me 32 electrons. So 32 electrons. The simplified or the easiest structure there is going to be that with a minus 2. So technically that would be one of the resonance structures. So I can count that one as a resonance structure because it is a valid dot diagram this time because it does have everyone with their octet. And I've used up all 32 electrons. All right, now an octet or a resonance structure of this is the fact that sulfur is in the third row of the periodic table or lower. It can hold more than 8. So I can take these extra pairs of electrons and put them in the bond maybe once, twice, 3 times, 4 times if I want to. I'm going to do it, let's say, once to start with. So I'll do a double bond there. And maybe I'll do it again twice. So I'll make it with 2 double bonds like so. So now for formal charge, I can do formal charge on each of these, and this time evaluate which of those would be the best structure. All right. So we can do sulfur in the middle, or let's do these single bonded oxygens. Well, singly bonded oxygens are always going to be the same. 6 for the free element minus the 6 dots that are around it plus half of the bonded, and so all of these are going to be minus 1s. And then the one in the middle, the sulfur in the middle, is going to be 6 minus 0 plus half of 8, which is 4, so that's a positive 2. Remember, your charges must add up to equal the overall charge of the molecule, which in this case is a minus 2. When I do this one, I get a minus 1, a minus 1, a minus 1, and a doubly bonded oxygen, which, from right there is a 0. So then this time I could see that the sulfur in the middle is going to end up being a positive 1, but I should show it. So I have 6 minus 0 plus half of 2, 4, 6, 8, 10, which is 5, so a positive 1. And then this one's going to give me a 0 there, a 0 there, a minus 1 there, a minus 1 there, and a 0 there, so that I end up with 3 zeros. So this would be the best because it had the most zeros for the sulfate. I really don't want to do any more of these. I'll do CO3, and then I'm going to call it a day. So 4 plus 18 plus 2 is 24 electrons. When I do carbon in the center, I have 3 oxygens. Finish the octet of the oxygens, and I use up all 24 electrons. And so there's my skeletal one this time, which is not a valid Lewis structure. Why? Well, because carbon only has 2, 4, 6 around it. So just like the nitrate ion in the first one, I'm going to do a double bond on the left, a double bond on the bottom, and a double bond on the right. Each of those considered a different Lewis structure. That should be a carbon. And I can use an eraser. So carbon on the bottom, double bond on the bottom, and a double bond on the right. Now for this one, unlike the one above, I can't have more than 8 electrons around the carbon because carbon is only in the second row of the periodic table. Remember, in order to have more than 1 or more than 8 around the central atom, it has to be in the third row of the periodic table, the third period or lower. All right, so that's it. I quit. If you need those last 2, I'm going to do them after I turn off the video, and then I'll just post this review sheet on my website. Okay, good luck.